All right, let's talk about More Agents is All You Need, another paper with a very original title. This paper is kind of interesting from the perspective of they noticed something in the literature, then they tried it, they noticed something that, oh, I wonder if this simple thing would work. They tried it and they ran a bunch of sort of comprehensive experiments, and it turns out that the thing they noticed worked. So they published about it. And it's kind of cool. Um, So the main idea is that if you have a task that is difficult for an LLM to complete, you can throw more LLMs at the same problem and the performance will be better. So just by adding more agents, asking many agents the same thing, and then doing majority voting at the end to pick the final answer, you get better performance. So nice illustration of this is here. So they have these sort of four models here in complexity, in the order of complexity. So Llama 2 13 billion is the sort of smallest and worst performing model. Llama 2 70 billion is a little bit better. GPT-5 3.5 Turbo is a little better, and then GPT-4 is even better than that. And what they demonstrate is that let's say you're using Llama 2 13 billion, you start, if you just use one agent, your performance is over here, versus Llama 2 70 billion is up here. But if you take 15 of these smaller llamas and ask them into majority voting, you get the same performance as a single 17 billion llama. And if you take 35 of these 13 billion llamas, you get better performance than a single llama. And that scales with other models as well. So if you take a GPT 3.5 Turbo, interestingly, you don't quite get to GPT-4 performance, but you get closer. So that is interesting. And that's basically what the whole paper is about. There's sort of much more experiments and justification about this. One of the sort of high level thing that's interesting to mention is that there's a bunch of related work that did similar things before. But this paper, they don't say it explicitly, but they basically say all this other work is way too complicated. You don't need any of this complex stuff. Just throw more dumb agents at it, and your life will get better. They also say that what they're showing here is compatible with these other more complex methods, so you could do both. But it is interesting to see this sort of how they divide previous work into three different categories. So one is LLM self-ensemble, which is kind of similar to this, but and you have a single model, and then you create different prompts for sort of different instances of the model. You ask the same question and you get an answer, and then you do majority voting. What they're doing here is kind of a simplified version of that. Just sort of not even different prompts, it's the same agent. I guess the temperature might be set so that you get, every time you ask the question, you get a slightly different answer. Then you do majority voting. Then slightly more complex is heterogeneous LLM ensemble. So this is also an ensemble of different LLMs, but instead of doing majority voting at the end, you do some kind of supervised learning run to figure out when to sort of listen to which LLM. So it's kind of an ensemble of agents approach where you ask the same question of multiple LLMs, but the LLMs are kind of distinctly different, and you have some trained procedure for figuring out who to listen to in which case. And then multiple LLM agents collaborating with each other. It's even more complex than that because you have multiple agents and they actually talk to each other. So like agent one says something, agent two says something else, and then they kind of talk about it. There might be multiple agents kind of involved. And in previous work, all of these things turned out to improve performance. But this paper is saying, yes, that's great, but it's way too complicated. Just throw more agents in it. So this is like they basically demonstrate the approach here. You have a query, maybe some query including prompt engineering, but maybe even without prompt engineering. You send it to like 40 different agents. Each one gives you an answer. You find the answer that is most similar to all the other answers, and you accept it. That's basically all there is to it. The rest of the paper is talking about how they evaluated it, what they compared with, and they also have some interpretations about why this works, like what kind of which properties make it work. I'm a little unconvinced about this isolation study because they kind of use the mathematical problem and claim that generalizes, and I'm not sure it does, but maybe it does. It's kind of interesting to read. In any case, very interesting paper. I like that it's sort of pushing simplicity. So thanks. Hope you enjoyed it.